Algebra 2 Honors 10.1 Day 1, we're looking at doing some sections on probability. And today we're in 10.1 Day 1, and you're going to be looking at writing up some sample spaces and finding some probabilities. And so what is a sample space? Well, here we have a probability experiment is an action or trial that has varying results. The possible results of a probability experiment are outcomes. For example, if you roll a six-sided die, there's 6 possible outcomes. And then a collection of one or more outcomes is an event, and such as rolling an odd number. A set of all possible outcomes is called a sample space. So in this first one, you flip a coin and you roll a six-sided die. And so how many possible outcomes are there? And then list those possible outcomes. Well, this fits what we call a general counting principle. And that general counting principle is if there's so many ways one event can happen followed by so many ways another, then their product of the number of each of those is the total number of outcomes. So in this one, it is you flip a coin. What they're talking about is it's heads or tails. So there's 2 possibilities for flipping the coin. And if you roll a six-sided die, there are 6 possibilities for that. So we expect that there are 12 possible outcomes. And then you need to be organized when you do the sample space, and of course you haven't really seen exactly what that's going to look like here. And a way to do that is by doing a tree diagram. You don't necessarily have to do one, but it is a good tool, especially in different cases, so that you don't miss any type of outcome. And so basically we're going to flip the coin first, so your outcomes are either heads or tails. And after the head, if you got a head first, then there'd be get a 1, 2, 3, 4, 5, or a 6. Or the tail, 1, 2, 3, 4, 5, 6. And there are 12 ends of those branches, which is consistent with 12 possible outcomes. And so your sample space is heads in a 1, heads in a 2, heads in a 3, heads in a 4, heads in a 5, heads in a 6, or tails in a 1, tails in a 2, tails in a 3, tails in a 4, tails in a 5, and tails in a 6. And that is your sample space. Another example, you spin the spinner and you flip a coin. How many possible outcomes are there in the sample space? Well, when you spin the spinner, you get a 1, 2, 3, or 4, so there would be 4 possible outcomes on the spinner, and if you flip a coin, it's heads or tails. There's 2 outcomes there. There's a total of 8 possible outcomes. And that says list them. And you might not need a tree diagram for that, but it would look something like you get a 1, 2, 3, or a 4. And after that, you flip the coin. So you get heads or tails with the 1, heads or tails with the 2, heads or tails with the 3, and heads or tails with a 4. So you get 1 and a head or 1 and a tail, 2 and a head, 2 and a tail, 3 and a head, 3 and a tail, 4 and a head, or 4 and a tail. And that is the listing of your sample space. All right, so find the number of possible outcomes and list the possible outcomes. Here, you flip 2 coins. Well, again, they're looking for its heads or tails, so there's 2 choices, the first flip and 2 the second, for a total of 4 possible outcomes. I'm just going to abbreviate that. And so it's heads and tails for the first, followed by, if you got heads on the first, you could then get heads or tails on the second. But if you got tails on the first, you could again get heads or tails on the second. So the sample space is heads, 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 tails, tails, heads, and tails, tails. And that's your sample space. Note that getting heads first and tails second is a different outcome than getting tails first and then heads. Those are two different possible outcomes. Monitoring progress number 2, you flip 2 coins and roll a 6-sided die. So this one, your number of possible, you flip 2 coins, and so there's heads or tails on the first, there are heads and tails on the second, and then a 6-sided die. That is going to be 24 possible outcomes. And so you need to be careful that you have a method so that you don't miss any. And so, again, we're going to start with heads and then tails, and from there we get heads or tails, heads or tails, and then off of each of these you're going to have those 6 outcomes. And so that's going to be true off of each of these ends, getting us with the 24. And I think that's enough to go ahead and write them out. You have heads, heads 1, heads, heads 2, heads, heads 3, heads, heads 4, heads, heads 5, heads, heads 6. Then you have heads, tails 1, heads, tails 2, heads, tails 3, heads, tails 4, heads, tails 5, heads, tails 6. And then if we would have started with tails, tails heads 1, tails heads 2, tails heads 3, tails heads 4, tails heads 5, tails heads 6, and then lastly tails, 2 tails and a number. So again, it's can get big in a hurry, but have an organized way so you don't miss anything. So there's some ideas of writing out sample spaces. Then we have theoretical probability and probability of an event, which we will write something like P of A, where A is an event of, say, rolling a die and getting a 2. The probability of any event must be between 0 and 1. It can't be bigger than 1. It can't be negative. It can be 0, meaning it won't happen. It can be 1, meaning it happens 100% of the time. And it can be expressed as a decimal, a fraction, or a percent. So frequently we'll write them all 3 ways and box that as our answer for this lesson in this textbook. So anyway, theoretical probability is just the number of favorable outcomes over the total number of outcomes. So what's the probability of getting a 2 when you roll a 6-sided die? Well, your sample space is just 1, 2, 3, 4, 5, or a 6. And so how many ways can you get a 2? 1 out of how many in the sample space? And your probability of getting a 2 is a 1/6. That's, the theoretical probability. So theoretically, out of every 6 rolls, you should get a 2 once. That will be different when we get to actually experimenting. If you actually roll the die 6 times, you might not get a 2 at all. You might get it more than once. So that's experimental. Right now we're talking about theoretical. Theoretical is there's 1 chance of getting a 2 out of 6, so that is your theoretical probability. All right, so this attending to precision we're going to look at after we read example 2 here. In example 2, a student taking a quiz randomly guesses the answers to 4 true-false questions. What is the probability of the student guessing exactly 2 correct answers? Well, we need the number of elements in the entire sample space, and then we need, of those, how many have exactly 2 answers correct. And this is important because when it says exactly two, that phrase is more precise than saying two answers, which could be interpreted as at least two or exactly two. And so we have exactly two, so we don't include where there's 2 or 3 or 4 correct answers. So anyways, so the sample space on this is kind of crazy. So, because we're going to have 4 true and false questions. So there's 2, you can get true or false on the first, true or false on the second, true or false on the third, and true and false on the fourth, for a total of 16 possible outcomes in the sample space. And if I try to create that, then I get the correct answer or the incorrect answer. And from that, I get a correct or an incorrect. And from each of those, I get correct or incorrect, correct or incorrect, correct or incorrect, correct or incorrect. And from each of those, I get correct or incorrect, correct or incorrect. It's easy on this one to miss something. So sometimes that tree diagram can just help you organize, because then I just read through that first set of branches, and that's one outcome, correct, 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 correct. And then I read through another set of outcome, I go through that same one, correct, 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 and then to incorrect. And I just go down the line that way, and I don't miss anything out. So my sample space is correct, 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 incorrect, correct, correct, incorrect, correct, 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 incorrect, incorrect. And that takes care of that top branch and a couple of outcomes after that. And so then if I switch and go correct, incorrect, correct, correct, and start off that way, I've got correct, incorrect, correct, 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 incorrect, correct, incorrect, correct, incorrect, incorrect, correct, correct, incorrect, incorrect, incorrect. It gets to be a lot. So from there, then I am ready to start here. Incorrect, correct, correct, correct. And then I'm ready to start this branch. And that is my sample space, and there are 16. So what's the probability of getting exactly 2 correct answers? And this is my theoretical probability. I have to look through this, and I know there's a total of 16, but how many of them have exactly 2 correct? So if I go through here, exactly 2, there's one. There's another. There's another. Here's one. Here's one. Here's one. And then you want to kind of double check. To see if we've missed anything. But it looks like there are 6. So 6 have exactly 2 correct, or that is 3/8, or which is about 0.375, or 37.5%. And just you can just put all of those, and there you go. So an extra example like this, a coin is flipped 4 times. Was the probability it lands on its head exactly 3 times? Well, it's going to look a lot the same, because if a coin, it's heads or tails, and you're flipping it 4 times, so that is going to be a total of 16 possible outcomes. And so we've got heads, tails, heads, tails, and from each of those, again, you need an organized system for writing out your sample space. And I think tree diagrams help with that a lot. So similar to the previous example, you just get at it, get it done. It's not quite as bad. Yes, it's a little tedious, but you can kind of get into a pattern of how you see it. And it gets a little faster. And that is your sample space. So now, that theoretical probability is the number of times, in here we have exactly 3 heads. And so lands on heads exactly 3 times. There's 3. Here's 3. 3. 3. And that's it. So there are 4 chances out of 16, which is 1/4, which is 0.25 or 25% of the time. Right, moving on. The sum of the probabilities of all outcomes in a sample space is 1. So if we went back and you could have 1 head, 2 heads, 3 heads, or 4 heads, those, if we were just looking at heads, those probabilities, if I looked at those, exactly 1, exactly 2, exactly 3, exactly 4, they would add up, or 0, I'd need to include, those probabilities would add up to 1. So the sum of the probabilities of all outcomes in a sample space is 1. So when you know the probability of an event A, you can find the probability of, we call the complement of the event. And the complement of event consists of all outcomes that are not in A. All outcomes that are not in A. So for example, we're going to roll a 6-sided die. And I'm going to let event A be getting a 2. A complement is not getting a 2, means it's getting anything but a 2. So a complement of event A consists of all outcomes that are not in A, and it's noted by a bar. So this is A with this bar over it, a bar. So right now, the probability of A plus the probability of A bar, since A bar is everything except for event A, those will total 1. Or we like to use it, probability of A bar is 1 minus probability of A. And that is this formula that you want to know. You want to know that A bar is called a complement. You want to understand what a complement of an event is. And so, writing probabilities of complements. When two six-sided dice are rolled, there are 36 possible outcomes. Find the probability of each event. So here, they're showing you where on one of the die, you're getting a 1. And then on the other, the red die, you're getting a 1, 2, 3, 4, 5, or 6. So this is, or this is a 2 on the white, or a 3, or a 4, or a 5, or a 6. So they're showing you all the different possible outcomes. You've got 2 different dice that you can tell the difference between, and there are 36 possible outcomes. I like to, since we're talking about the sums, I actually like to create this other chart. Although you can see it in this one, I encourage students, when we're talking about finding probabilities of sum when you roll 2 dice, to create this one on their paper. It really doesn't take very long. So it's just the idea that right here, 6 plus 1 is 7. So I just totaled it because we're looking at their sum. The second roll, 1 plus 2 is 3. And so these sums start looking like this. And those are the 36 different possible sums. And so right here in part A, we want to know that the sum is not 6. And so if I let A be sum is 6, then A bar is sum is not 6. And using the complement is kind of nice when it is composed of a lot of other types of events. Not getting a 6 is 2, 3, 4, 5, 7, 8, 9, 10, 11, or 12. That's sum is not 6. There's a lot of different things we have to look at. However, if I use the complement and get the probability of the sum is 6 and subtract it from 1, that's going to be a little bit easier. And so in this case, the probability of A bar, which I'm letting be the sum is not 6, is 1 minus the probability of A. So probability sum is not 6 is 1 minus the probability the sum is 6. And in the chart, if I look at where the sum is 6, I'm just going to highlight that there. If you count those up, there are 5 of those where the sum is 6 out of 36. And that's easier than counting up all the other ones where the sum is something other than 6. And that 5, 6, 1 minus that is 31 out of 36, which is about 0.861, or 86.1%. Okay, part B, the sum is less than or equal to 9. Well, if I want to use complements on that, the sum less than or equal to 9, the complement of that is that the sum is greater than 9. So I'm going to let A be sum is greater than 9. And so I can say that the probability that the sum is less than or equal to 9 is 1 minus the probability that the sum is greater than 9. And there's fewer things to count for the sum is greater than 9. If I go here and try to just erase that, where is the sum greater than 9? That would just be those 6 opportunities there. 3 sums of 10s, 2 of 11, and 1 of 12. And so where the sum is greater than 9, it's 6 out of 36, which gives me 30 out of 36, which is 5/6, which is about 0.833 or 83.3%. All right, extra example 3, the sum is greater than 8. Well, greater than 8, I don't know if it's worth doing the complement on it. Just trying to get rid of those highlights without erasing numbers. Almost did it. All right, so sum is greater than 8. It's just where it's 9, 10, 11, 12. I think I would probably just not use complements. I would just count those up. And sum greater than 8, there's 4 9s, 3 10s, 2 11s, and a 12. And that is a total of 10 out of 36, which is 5/18 or 0.278. The sum is not 2. Well, there's a lot other than not 2, so I'd rather use the complement and let A be the event, the sum is 2. And so A bar, the sum is not 2. So the probability of A bar is 1 minus the probability of A. And the sum is 2. There's only 1 out of the 36 where the sum is 2. So that's going to be 35/36. And so that comes out to about 0.972. And this last example, using area to find probability, you have to actually find areas of geometric figures. You throw a dart at the board. Your dart is equally likely to hit any point. So, it's randomly going to hit this squared dartboard, and it's not going to land outside it, and every spot is equally likely. So that's a little bit crazy, but that's important in terms of, if you're a good shot, then that changes the outcome. And that's a dependent outcome on your skill. And that's not what we're talking about here. So anyways, you throw a dart at the board shown. Your dart is equally likely to hit any point inside the square board. Are you more likely to get 10 points or 0 points? So we need to find the probability of 10 points and the probability of 0 points. And the probability of 10 points is going to be the area of that small inner circle where you see the 10. And the 3 is pointing to each segment in there is 3 inches, so that the radius of the largest circle is 9, the radius of the smaller is 3. And so the probability of 10 is that area, so the probability of circle of radius 3 over the probability of hitting the square. And so we use the areas of that. And so the circle is going to be pi times radius squared, pi r squared. Probability of the square, well, from here to here is 9, but the whole side length then is 18. It's an 18 by 18 square, so area of a square is side squared. And so we get 9 pi over 18 squared. And I'm not multiplying that out because 9 goes in 18 twice. You get 2 times 18 on the bottom, so that's pi over 36 for the exact theoretical probability. And if you put that in a decimal form, you get 0.0873. probability of 0? Well, to get the probability of 0, you've got to get that outer area that's in the square but outside the largest circle. And then put that all over the probability that it hits the anywhere in the square, which is that 18 squared. So you have to find that probability, or I should say, the area of square minus area of circle, radius of 9. That largest circle has a radius of 9, and I have to subtract that out to get that shaded area on the in the corners. And so the probability of 0 is 18 squared minus 9 squared times pi all over 18 squared. And that's a 324 minus 81 pi all over 324. You cannot cancel the 18 squares in the step before or the 324s because you have subtraction in the numerator. But it does happen that 81 goes into 324 and 81. And it goes into 324 4 times. So that right there is your exact probability. And if you work it out to 3 decimal places, 0.215. That's it.